the acceptance probability during these random walk Metropolis Hastings algorithm, and they monitor the acceptance probability to make sure that we're not accepting too often or accepting too little. Okay, and the final example that I will talk about of proposal density for Metropolis Hastings algorithm is the Gibbs sampler. So suppose that our space, our state space X, or X is multivariate. The Gibbs sampling algorithm iteratively samples Xi given all of the other, whoops, this is a typo, that should be D there, not N. So it samples Xi given the state at the current value of all the other X's. So this distribution, the density of Xi given all the other values is known as the full conditional. So the chain proceeds by, well, we initialize at some value X naught, and then we iteratively sample. So we sample X1. So we sample our new state xt plus 1 from the full conditional of x1. Then we plug in this value to the conditional density. We sample x2 given all the other states. Again, we plug this in so that for the last dimension of x, we sample xd given the updated values of all our other variables. So you can show that this Gibbs sampler is a special case of the Metropolis Hastings algorithm where the proposal is always accepted. Okay, so let's see an example of Gibbs sampling. Let's consider the bivariate normal again. So in this case, we know we've seen, yesterday we reinforced a lot of the properties of Gaussian distribution. So we know that if X is a bivariate normal, then the conditionals are also bivariate normal, which are linear in the state that I'm conditioning on here. So we just proceed by sampling X1 from a normal, and then we plug in our updated value of x1, and we sample x2 from a normal distribution. So what's going on here is that we have, so say we start here at x naught. We sample x1 given x2, so it'll roughly be in here. So say we get some value here. Then we sample x2 given x1. It'll roughly be between, in this interval here. And we keep repeating this to get samples. So you can see that if there are strong correlations, so if the bivariate normal is described by this ellipse here, the mixing can be quite slow. So instead, if I have a bivariate normal, which has described by a very elongated ellipse, then if I want to move from one state to another state, it can take a lot of steps to explore the entire space. So in summary, this means that strong correlations between our variables can slow down Gibbs sampling. So if any of the groups of variables can be updated jointly, we can improve the mixing, and this is known as blocked Gibbs sampling. If you work with Gibbs sampling, another thing that's often done, it's called hybrid Gibbs sampling. That's if one of these steps here, we can't actually sample from the full conditional, and we need a Metropolis Hastings step here to sample from the full conditional at that stage. Okay, convergence of the MCMC. So samples of our chain need to be discarded so that we have approximately independent samples from our target density P of x. So this is done in two ways. The first is called burn-in. So to overcome poor initialization, we often throw away the first, say, T0 samples from our Markov chain. And the second is thinning. So we may often only keep every kth sample to reduce the dependency in the Markov chain. But it's often very difficult to monitor this convergence. We can tell whether there's lack of convergence through various diagnostic measures. So one thing that's often done is by looking at the trace plots. So the trace plots just plot the samples, so as iterations versus our samples. And what we want to see, a good mixing of a Markov chain would just jump around and stabilize around some current value. So if we see something like this, so this is the iterations, and this is our sampled values of x. If we see something like this, we may see that we roughly need at least a burn-in period here. So we'll need at least to discard these first, say, T0 samples. Another thing that's done is looking at the autocorrelation plots. So we'll see this in some examples in the next slides. So this just it measures the correlation between xt and xt plus k. So we want to have approximate dependent samples, so we want autocorrelation plots which have low dependence. So this is at 0, and then what we'd like to have is no dependence afterwards. So this is the lag, and this is the autocorrelation. Another thing that you can do is compare chains with different initialization points. So here's an example of that. So if we compare, so say we start our chain at 0, that's the red chain, chain 2, or we start our chain at 1. We'd like the behavior of these chains to be similar. So if you look at this plot, you can say that convergence has not been reached for our Markov chain. Instead, for this plot, well, we can't say anything for this plot, but if you look at this, you could say we probably need at least a burn-in period of, say, 1500. So in general, with MCMC, this is a big issue of MCMC, trying to tell whether the Markov chain has converged or not. And there are other diagnostic tools which have been developed that you can look at. So in summary, MCMC is a very general method. It's applicable to many problems. It's easy to implement. And we have theoretical guarantees as our number of samples goes to infinity. So as our number of samples goes to infinity, we know we are guaranteed to sample exactly from our target distribution P, as opposed to the approximation methods that we saw with Miguel that time. In those cases, we are approximating our true density with some other density. So the disadvantages of MCMC are that it can be slow and expensive to compute, and it's difficult to assess the convergence of the chain. Okay, so now let's go back to Bayesian inference. We just talked about these MCMC algorithms. What does this have to do with Bayesian inference? So in Bayesian inference, often a closed form for the posterior distribution is unavailable. So in that case, our target is P of theta given x, the posterior of our parameters given our data x. So MCMC can be used to obtain samples from our posterior. Then from the theory on Markov chain Monte Carlo, we know that this expected value can be estimated by just plugging in our samples at g to the function g and taking the average. So this means, for example, that we can approximate the posterior distribution with just, so if g is just the indicator that theta t is in some set A, we can approximate our posterior distribution with point masses at our samples with weight 1 over t. And for example, if we're interested in the predictive density at x star, well, this is just equal to the integral of p of x star given x and theta. So the predictive density is just equal to the integral of x star given theta x p of theta given x d theta. This often doesn't depend on x here. So this we can just write as it's the expected value with respect to the posterior on theta of this, of our likelihood. So this thing we can estimate here. So we could just get an estimate of our predictive distribution based on our MCMC samples. Okay, so I have 2 examples. So the first is, both of these examples we saw with Miguel last week, so let's see how we can use MCMC methods to obtain inference for these examples. The first is probit regression. So in this case, yi are Bernoulli distributed, so they're either, our output observations are either 0 or 1, and the probability that y is equal to 1 is just, well, we have a linear function of x, and then we map this function on the real line to the unit interval through the probit transformation. So this is the standard normal distribution function, phi. Now we need a prior on our parameters, so these are our weights here. We can assume that the weights are normal with some mean and variance covariance matrix. Now, an alternative representation of this model is by introducing a latent variable yi tilde. So if yi tilde given x and w, if these are independent, normally distributed with this mean, so this is just the linear function and unit variance, and we just set our observed values of y to the indicator that our yi tilde is bigger than 0. Then if we integrate out yi tilde, we recover our original model here. So this is just representing this model by introducing this latent variable yi tilde. And this latent variable yi tilde will be the key for the Gibbs sampling algorithm that we'll see on the next slide. So the Gibbs sampling algorithm proceeds by initializing our weights and our latent variables y tilde. Then we sample the weights conditional to the latent variable y tilde and x. Well, so actually, so step 0 is to initialize w and y. Step 2 is to sample W. So we sample W from its full conditional. So W given everything else, which is y tilde and our data, x and y. So this is just proportional to our prior on W. And P of y tilde and y given x and W. This joint density of y tilde and y we can write as the product of the marginal of y tilde given x and W and the conditional of y given y tilde x and W. This thing here, y given y tilde, it's just the indicator whether y tilde is bigger than or equal to 0, right? That line there. So this term goes away, and then we just have that this is proportional to our prior on W and the likelihood of y tilde given x and W. So this is just a normal. This is our prior, and this is the product of normals with unit variance. So we saw this updating rule yesterday. So the updated, this means that W is normal with some updated mean and variance. So this looks very similar to what we saw yesterday. It's just the updated mean and variance from the normal density. Okay, so step 2. Step 2 is to sample y tilde from its full conditional. So y tilde given W, y, and x. So this is proportional to y tilde given W and x, and y, the density of y given x, W, and y. So this, we said, this is just a product of normals. Unit variance. And this is just the product of indicators. So yi tilde must be bigger than 0 if y is equal to 1. So yi tilde must be bigger than 0 if y is equal to 1. And yi tilde is less than 0 if our observed y is equal to 0. So you see here that these yi tildes are conditionally independent with a truncated normal distribution. You see that? So we can just sample each yi independently with a truncated normal distribution. And this is typically done here using the integral transformation method, the first method that we saw. Okay, oh, we're almost out of time. So I'll just show you the results of one example. So this, I simulated some data based on the true model. So here's I did 10,000 iterations. Here's the trace plot of the first 2,000 iterations. This is for the intercept term and the slope term. So you can see that I initialized it at 0, 0. In this case, our chain jumps to the stationary distribution pretty quickly. We can say that the mixing looks pretty good in both of these cases. Here's the autocorrelation plot. So this estimates the correlation between xt and xt plus k for different values of the lag. So we'd like something that drops off pretty quickly. So here we see that there's some dependency in our chain, but it's not too bad. Sorry. The lag, so this is like the correlation between xt and xt plus k. So k is that lag. So this would be the correlation between xt and xt plus 1. That one.
And may I ask again, like, you should look at these graphs during the iterations, right?
No, you usually look at this after so you run, say, so you run it for, say, you can run it for just to see how your method is doing, say for 1,000 samples. You can look at your trace plot, see how things look, how the mixing is, and you can also estimate the autocorrelation plot. And again, the aim would be to have something that drops off to 0 pretty quickly here, and something which is moving around the space. And you want something where the mean is stabilized around some value here.
Yeah, I thought that you're doing graphs to see what's the thinning parameter, you know?
Yeah. You can look at these plots to see what the thinning parameter is. These plots to see what the burn-in period should be. Okay, so this was the data that I sampled. I sampled 100 data points. So we have the crosses were zeros and the circles were ones. So the black line is the true probability that y is equal to 1 as a function of x. Since I simulated the data, I know the true. I simulated the data based on, I picked some values of W0 and W1. So this is the red curve is my true probability. The black line is my estimated probability that y is equal to 1 given x and w. So that is just equal to expected value with respect to w. So that's just 1 over t. I average this by plugging in my samples. Okay, so the black line is my estimate. In this case, we have a pretty good fit here to the true. And these dashed lines give the point-wise 95% credible intervals. So we have that, we could consider this thing here to be a random function. This, we say p of x. This could be a random function taking values in the unit interval. So it's random in terms of w. And its distribution we can describe with point masses at this function sorry, that's WT, with WT plugged in. So one way to summarize this distribution of P of x is through the expected value, the black line. Another way to summarize it is with the 95% credible interval. So that's the point. So fixing x, I can calculate the 95% credible intervals. I have t samples. What I did was I just sorted the values, and I took the 2.5%. So the credible interval here. Oops. So the credible interval is the interval such that the probability that our function lies for some fixed x lies within this interval with 95% probability. So we can find A1 by saying that this probability must be 0.025, and the probability that so we can just do this by sorting our observed samples and taking the t times 0.025 value to estimate the credible intervals. Okay. Oops. Okay. Okay.
Thank you, Sarah. Thank you for the lecture. So, do you have any questions? Quick questions we can handle? Or should I leave it for tomorrow? If you have any questions, you can look into the lectures and again, if you have any questions, you can ask tomorrow. Okay? Okay, so thank you. Thank you, Sarah. And see you tomorrow.